All right. Hey, everyone. Today was day 18 of Advent of Code. Today was an interesting puzzle again that needed some tricks to solve, at least for me. So let's have a look. So our input is a list of instructions such as those. And for part one, the third part does not actually matter. So all the important instructions are the first and the second part. And the first part will tell us a direction. So up, down, left, or right. And the second part is how many steps to go in this direction. And then if we follow those instructions, we'll get some path, so something like this. And it should start and end at the 0 position. And then what we want to know is how many positions are within the path, so on the path and as all the positions within. And that's what we need to figure out for part one. So how can we do this? So passing the input in this case is not too hard. We just convert the distance into an integer and the direction is already as it is. And then for the solution, we'll consider positions, this time as a tuple of two ints again. And then we are told the direction, so up corresponds to leaving the x coordinate unchanged and subtracting 1 for the y coordinate, and down corresponds to leaving the x coordinate unchanged and adding 1 to the y coordinate, and so on. This dictionary will allow us to get a new position based on the current position and the direction. So we just get this change in x coordinate and y coordinates from the dictionary, and then the new position will be x plus the change in x coordinate times the distance, and y will be similar. And with this, we can find all the positions of a path from a set of instructions or list of instructions. So we just start at 0, 0, have this set of path positions, and then we go through all the instructions, and then we do as many steps as there is distance, and in each step we update the current position, and we then append the current position to the path positions. We can check that we actually end up at the beginning again, but yeah, that will give us all the positions of the path. And then we're ready to count all the positions in a path once we have this path representation. And for that, it's actually easier to count all the positions outside the path. And for that, we'll take our minimum x considered in this part as the minimum x coordinate in the y in the path positions, but we subtract an additional one, so all the outside positions are connected, and similar for the max and for the minimum y coordinate. Then what we'll do is we start with an empty set for the outside positions, and our first queue will just have one particular outside positions in it. So we know that because we subtracted minus 1 for the minimum values, that these position will definitely be outside the path. And then what we do in each step is we get a particular position from the queue, and then first we check if this position is in the path positions, in which case it's not outside, so we continue. Otherwise, if it's already in the outside positions, we already considered it, so we can continue. We don't need to consider this case. And finally, if the x and y coordinates are outside these min x and max x, this box given by this minimum and maximum values, then we're also not interested in continue. And if none of those is true, then we found a valid outside position. So we add a position to our set of outside positions, and then we add all the neighbors to the queue. So we just go through all the direction values and update the x and the y based on those change in x and y, and add this point to the queue. And then once our queue is empty, we should have found all the outside positions, and that kind of allows us to find the number of inside positions fairly easily. So the total size we can just calculate, and then the count within will just be the total size, and we subtract all the number of outside positions. All right, that lets us solve the problem. So we just, for our lines, we pass the lines into this list of instructions. Then from that, we get all the positions of the path, and then we count the positions within the path, including the path in this case, and that would be a solution. So we should run it on the test input to see whether that actually works out. Looks good. So we can also run it on the real input, and it also turns out it gives us the right solution. For part 2, it turns out actually not the first two parts were the instructions, but the last two was the only important part. So this last string, or part of the string, actually tells us the directions as well as the lengths. So in particular, this substring will tell us the distance in base 16, and the last digit will tell us the direction by this encoding that sends 0 to right, 1 to down, and so on. Okay, and so The parsing is relatively straightforward. We just convert the substring to an integer by use base 16, and the direction we also convert into this letter that we used in part 1. However, this means now in part 2, the numbers are much bigger, so we cannot just solve it as in part 1, but we need to be a bit smarter. So first we'll use a different representation of the path, so we'll represent it by the corners it goes through, so each position where it turns essentially. And we need to get the list of corners from a list of instructions, so that's fairly straightforward. We just started the position 0, 0, and then for each instruction we get a new position based on the current position and the direction and the distance we need to go. And this will give us the next corner. We append this to the list of corners, and that will allow us to get all the corners. And now what we want to do as a first function will be helpful is count the number of inside elements within a line. So it is a bit difficult in this line, for example, when there is some corners are actually in this line, then it's difficult to count the number of elements within because there's many different scenarios. So we won't do that for now. But if there's no corner within a line, then it's much easier to count the number of inside elements. It's very good for this line, for example. If you look why this line, if this is the path, we can just consider each point or where the path intersects the line. So it will be this coordinate, this coordinate, this coordinate, this coordinate, and then all the inside elements will just be between the first and the second intersection and between the third and the fourth intersection and so on. So for a line that does not have a y-coordinate of a corner, it's fairly easy to count the number of inside elements. So that's what we do here. First, we need to find all this intersection. For that, we go through all the corners, and we have like a previous corner, and we have the two corners of the line. And then we check if the x-coordinates of these two corners agree, then that means the line is vertical. Then we check if the y-coordinate of the line is between the minimum and the maximum of the y-coordinates. That means this particular path, part of the path intersects the line, and we add the x-coordinate to this list of intersections. Then we sort them by size, and then all we have to do is go through each of those pairs and count the number of elements within those two intersections. So if we have a start x and the end, if you have the start x and the end x, the number of intersections, the number of elements within will just be the end minus the start plus 1. Okay, so that let us count the number of elements within the path in a line such as this. So the other lines are a bit more complicated. So what we do as a first start, we'll remove all the easy lines or most of the easy lines. So since the number of corners is much less than the size of the whole grid, removing all the easy lines will allow us to reduce the size of the grid by a large factor. So it will make the remaining problem much easier. So I can remove the easy lines. So the easy lines are essentially those which have no corners inside them. So what we will keep track of is first we need to keep all the y-coordinates of all the corners, and we'll sort them by size. And then we will have a count which tells us how many inside elements we removed by removing those lines. And also we have a dictionary that will tell us how to map the old y-coordinate to the new one. And for the very first y-coordinate, it was just map to 0 kind of arbitrarily. And then we go through all those y-coordinate and also consider the next y-coordinate. In the first case, if they're only one apart, then we can't remove any lines in between. So we just update the dictionary and continue. Otherwise, what we can do is we consider the line after the particular current y-coordinate and count the number of elements within in this line. And now it turns out, or it's true that between this y-coordinate and the next y-coordinate, any line will have exactly the same number of inside elements. So we can use that to easily update our counts. So we consider the number of lines in between the current y and the next y. And then we remove actually all but one of them. So then the count we add is the count in a single line times the amount of lines we remove. And then similarly, we can update this dictionary. So since we keep one of those easy lines in between the two lines of y and next y, the new version of the next y will be 2 larger than the new version of the previous y. Okay, so that will allow us to remove all the easy lines, and we just update our corners finally. So we go through all the x and y coordinates of the previous corners and just use a dictionary to find the new version of the y coordinate. So this function will allow us to remove all the easy lines, and it also we kept track of the count, how many inside elements we removed by applying this function. So you can use that to solve the problem. So first, of course, for the lines, we pass the input and get a list of instructions. Then we get our corner representation from this list of instructions. And then we remove all the easy lines from this corner representation. That will give us the first count and a much smaller path that's still left to consider, how many positions that within the path for these corners. We also want to remove all the easy rows. So instead of writing a new function, we can just flip the coordinates of the current corners and change x and the y position. And then we can remove the rows of this path by removing the lines of the updated list of corners. And that will again give us a count how many inside elements we removed and a new much smaller path, which is represented by the corners. And then this much smaller path we can solve as in part 1. So for that we first need to convert these corners into the path positions that we used in part 1, and then we can call the function from part 1 in order to get the final count, what's still missing, what we haven't counted yet. And then a solution will just be the sum of all these 3 counts. What we removed in the first part, we removed in the second, what we removed by removing all the lines, what we removed by removing all the columns, and then the remaining part. Okay, and of that, we should, of course, test this code on the test input. That looks good, so we can also run it on the real input, and it also turns out it gives us the right solution. All right, that's it for day 18. I hope you enjoyed today's puzzle. Best of luck in the future, and I'll see you around.